Hi, my name is Aaron Sampson. There was a time when computers were simple, at least by modern standards. You had a box, a keyboard, and a mouse, and a monitor. Other peripherals were optional and not nearly as common as they are today. In this course, I'll introduce computer devices and components, beginning with the basics of computer networking. Then I'll explore various peripherals, including setup steps and installation types. Finally, I'll dive into the insides of computers with an overview of motherboards, BIOS and firmware, CPUs and RAM, storage types, cooling systems, and network interface cards or NICs. Upon completion, you'll have built a foundation for the basics of IT. This course helps to prepare learners for the CompTIA IT Fundamentals or ITF Plus certification exam, FC0 U61. In this presentation, we'll provide an overview of the basic characteristics of computer networking, which quite simply is any collection of connected systems, allowing them to communicate with each other over a wired or a wireless connection, which in turn allows them to share information such as files, email messages, instant messages such as chats, print jobs, and many other types of communications. Now, regardless of the type of network, they all require the proper hardware and software services to create the infrastructure that we use to take advantage of networking, which typically include routers, switches, cabling or wireless transmissions, and a variety of network services so that devices have the means to communicate in the first place. So, what typically defines the boundaries of a network? Well, they're usually based around geography, in that computers that are physically close together, such as those in the same office, will generally need to communicate with each other. But there is a lot of flexibility in my use of the phrase physically close together. For example, if you walk into any office and see, let's say, 50 to 100 computers, then almost certainly those computers will all reside on the same network. But there could be another office on a different floor of that building with another 50 to 100 computers that also reside on the same network. And even that's just a small example. In short, there can be any number of determining factors when it comes to defining a network. It really just comes down to which systems need to communicate with each other, and if necessary, the network that connects them can be as large as it needs to be, up to and including systems that are on opposite sides of the world from each other. Now, using those examples, the computers that are in the same office space reside on what is referred to as a local area network, or a LAN, whereas the systems that are on opposite sides of the world from each other would be on a wide area network, or a WAN. The net result of each type is the same, in that devices are still able to communicate with each other regardless of how far apart they are, but different technologies and communication methods are used in a LAN versus a WAN. Large enterprises with many locations around the world would have many individual LANs in each operating environment, but they would then likely interconnect each location with a WAN, so that every location would be able to communicate with every other one. The primary difference is that in the LAN, the organization would have complete control over all hardware used and all configurations. But in a WAN, while they can still implement the configuration they need, the hardware is often leased from telecommunications providers, and the physical connections themselves are also owned by those same providers. For example, if your organization has one location in, let's say, New York City and another one in Chicago, you clearly can't just run your own network cable between those locations. But large telecommunications providers have already implemented the infrastructure to interconnect locations that are just about anywhere in the world. So we simply pay to use that infrastructure. Now, another commonly used type of network is the wireless local area network, or WLAN, but as its name indicates, this is still a local area network. It simply uses wireless transmissions to carry data instead of physical wires, but the transmission range is not very far. I'm sure that many of you are likely using a wireless network even at home, but they're becoming more and more common in many environments due to the prevalence of wireless devices such as laptops, smartphones, and tablets. Now, while there are wireless WAN technologies, these would typically include satellite services that are simply not cost effective for most organizations, but they do provide access to very remote locations, such as to ships out on the ocean or aircraft in flight. Other common network types include the virtual LAN or VLAN, a metropolitan area network or MAN, and a campus area network or CAN. Now, a VLAN is actually just a method of using software to be able to create or reconfigure smaller networks out of a larger physical network, which helps to reduce overall traffic by keeping the systems that communicate with each other most of the time isolated from all others. For example, if you had 1,000 computers in total, but in 4 separate offices where most of the time each office only needs to communicate with other systems in the same office, then rather than creating a single network that hosts all 1,000 computers, you can use the exact same physical configuration in terms of having them all physically able to communicate with each other, but software on the switches can be implemented to dynamically configure 4 separate virtual networks, one for each office. This isolates each from the other, and there would be far less traffic within each VLAN overall. Metropolitan area networks are somewhere in between the LAN and the WAN. Too large for a LAN, but not really large enough to justify a full WAN. These might be used to connect offices that all reside in a somewhat smaller region, such as a downtown core of a city. And as its name suggests, the CAN would be used for something like a university campus to interconnect all of the buildings on that campus. Since they aren't as large as a WAN, organizations may be able to purchase and implement the appropriate equipment on their own, particularly in the case of a CAN, but many still rely on the existing infrastructure of telecommunications providers because it might still be difficult to interconnect 2 office buildings in a downtown core on your own. Other less common types include the personal area network or PAN, which is literally your own personal network using your own devices such as a phone and a laptop. These days, they're typically implemented using Bluetooth so that devices can communicate and or synchronize with each other, but the PAN is meant to service just your needs, no one else's. And a storage area network, or a SAN, is officially still a type of network, but it's dedicated to accessing very large amounts of high-performance storage, and they're usually only found in large enterprise environments. Collections of servers can all access very large arrays of hundreds or even thousands of hard drives, and any given server can access any given amount of that total space, but in a manageable size or chunk, and then use that space as if it was a dedicated hard drive of that server. So we, as standard users, don't really interact directly with SAN-based storage. Some of the main components of a network include what's known as the nodes, which, for the most part, at least in day-to-day conversation, refers to the individual devices that are connected to that network, such as a desktop computer, a laptop, a mobile phone, or a tablet. But in short, a node includes any connected device, including printers or fax machines, security cameras or sensors, and even the components that provide the connectivity in the first place, such as routers and switches. Now, we'll examine these devices in greater detail in an upcoming video, but in short, routers are the devices that allow communications to pass from one network to another, whereas switches provide connectivity from one computer to another. And that's an important distinction because you can absolutely build a single network using only computers and a switch. For example, if you have even just a small 8-port switch, you could plug in 8 computers and they would all be able to communicate with each other, so you have a network. But in order for that small network to communicate with another distinct network, most notably the internet, you must have a router. Routers allow communications to leave one network and enter another, but they aren't concerned with connecting individual nodes to each other. So while both switches and routers officially count, if you will, as nodes on any given network. As mentioned, switches connect computers together, and routers connect networks together. Now, just quickly, you might be thinking something along the lines of, well, wait a minute, I have a wireless router here at home, and all of my devices can use that to connect to each other, and I can connect to the internet. So, obviously, my router can connect computers together as well. While that is technically true, those types of home routers are simply switches and routers combined into a single physical unit. You could disconnect the cable that provides you with internet access from that device, and you would effectively still have a switch in that all devices connected to it could still communicate with each other, but none of them would have access to the internet. So again, they simply provide both services within the same device, but each type of service is distinct from the other. There are also two primary types of network architecture, which refers to the manner of implementation and/or which devices typically communicate with each other. The most common type in corporate environments is known as the client-server network, whereby most devices are clients, such as your desktop or a laptop, and then there are dedicated servers that provide us with access to resources such as files, print jobs, email, databases, applications, and intranet sites. So while any given client certainly can communicate directly with any other client, most of the time, any given client is communicating with some kind of dedicated server. The other type is the peer-to-peer network, which is much more commonly found in home or small office environments where dedicated servers either aren't affordable or just aren't necessary. Again, any device can still communicate with any other device, but there are no systems acting as dedicated servers to provide specific resources. Any given client on a peer-to-peer network could in fact act as a server if necessary. For example, if there is a printer attached to one system, it could be shared so that other devices could print to it. But any other system could do the exact same thing. So again, no single system is dedicated as a centralized device that provides most of the resources for the network. Finally, the network topology refers to the manner by which systems are physically laid out, so to speak, and they include the bus, the ring, the star, and the mesh topologies. Now, for the most part, the star topology is by far the most common, and in fact, I would go so far as to say that both buses and rings are almost entirely defunct, except for any special use cases, but just for the sake of knowing what they're all about, the bus is also referred to as a linear bus, and each computer was connected in line, so to speak, with a single cable run connecting each device using a type of connector known as a T-connector. So the cable could literally just connect to each side of the T-connector to form a single line. Then at each end, it was fitted with what's known as a signal terminator to keep the signal from bouncing back once it reached the end. As a real-life example, just imagine a straight-line train or a subway run with multiple stops along that run. Each stop represents a computer, and travelers can either get on or off at any given station. The ring is similar, but instead of two open ends, you simply close up the line by connecting each loose end to the other to form a ring. In this case, terminators are no longer necessary because communications just keep looping around the ring, and any given system can place data onto the ring at any given time. The star refers to the example I mentioned earlier, whereby there is a single central connection device such as a switch, and all computers are connected into that central device. It doesn't have to be laid out in an actual star pattern, but it's the fact that all communications go through that single central device. So using my train or subway example, this would be where all lines come together in a single place, and you can move from track to track. So this is what we see to this day because it scales far more easily than buses or rings, and quite simply, those topologies were among the earliest approaches to networking, and they were never able to achieve the speeds that we see today. Now, a mesh refers to systems that are connected to others with more than one connection. Now, they are still used, but usually not in the way that they were in the earlier days of networking. A mesh does allow you to create connections to multiple other systems, but in its earlier implementations, it required any given system to have multiple network adapters installed, one for each other system that it needed to reach. While reliable, it's very complex to manage this type of configuration. So these days, meshes are typically only used for systems that are very mission critical, so that if a primary connection fails, there is a backup connection available. So you might see them on very specialized servers or in some SAN configurations, but they're almost never implemented for standard client connectivity. Ultimately, we have come to depend on networks for just about every aspect of our daily lives, so it's important to have a basic understanding of their fundamental components and how they're implemented. In this video, we'll introduce some of the common types of network interfaces in use these days, which represent the physical device that allows your computer to communicate with any other on the network. But before we get to that, I also want to briefly mention the Transmission Control Protocol/Internet Protocol, or what is more commonly known as TCP/IP. This is the set of network communication rules, hence the term protocol, that provides connectivity at a software level by ensuring that each computer on any given network can be identified with a unique IP address. And I should quickly clarify that the address need only be unique on that network. In other words, you might see the same address in use on a different network, but it must be unique within the confines of your network. Provided any two systems that need to communicate each have a valid address, they can then exchange data packets, which represent the entire amount of data to be exchanged, but broken down into many discrete manageable units. Now, a more commonly known example of this method of communication is a simple phone call. If I want to call you, my phone must have its own unique phone number, at least within my area code, and yours must have one as well so that the telecommunications provider knows which devices to connect. Once the connection is established, we can begin our conversation, but there are still standard rules that we follow. For starters, we would both need to speak the same language, and we don't both try to speak at the same time. And when we do speak, we do so at a rate that is easily understandable by the other party. In other words, we don't overwhelm them with information. So the phone numbers basically equate to the IP addresses that uniquely identify our devices. The conversational rules we follow represent the protocols, and the entire conversation can be thought of as the complete transmission, but any given phrase or sentence can be thought of as the packets. But in order for any of that to happen, there needs to be a physical type of connection between the two devices to carry the data. So some common examples of those include the RJ11 connector and the RJ45 connector. Now, RJ stands for Radio Jack, and the reason why the RJ11 is included here is because this is in fact a type of connector that is still used today for some landline telephones. So this kind of comes back to my example of a phone call, but the RJ11 connector does not support the kind of speed needed by today's networks. It's really just used for voice, not data. Hence, the RJ45 connector is by far the most commonly used network cable connector, also referred to as an Ethernet cable. Now, without getting too far ahead of myself here, just quickly, Ethernet is simply the overall network architecture that defines the method by which information can be exchanged over the physical media being used. And in short, it defines a similar approach to what I just described when I talked about a phone call, in that while it's certainly possible for both of us to speak at the same time during a call, if we were to do so, the information would get all garbled up and neither of us would be able to understand the other. At its most basic level then, Ethernet defines that each device sharing the same physical media must each take its turn. In other words, I send, you receive, then you send, I receive. And if we both try to send at the same time, then the information is lost and we have to try again. So that said, while the RJ11 and the RJ45 both look similar, the 45 is physically larger and contains 8 small copper wires internally, whereas the 11 only contains 4. So as far as just about any standard network cable that is in use these days is concerned, you would almost certainly find an RJ45 connector being used. But of course, wired connections are not the only type of media being used. Wireless or Wi-Fi networks use radio frequencies instead of physical cables and have become almost ubiquitous due to the convenience and mobility they provide. But any given device that wants to communicate on a wireless network must still have a physical interface that transmits and receives those frequencies. Wireless networks are still Ethernet in terms of their architecture. They just use over-the-air transmissions in place of the physical wires. So even though there's nothing that you actually have to plug in, you still have to join the network by configuring your wireless interface to the appropriate settings. But wired and/or wireless Ethernet connections aren't the only method of networking available. Bluetooth is another wireless technology that has become nearly as common as Wi-Fi, at least for our mobile devices. And it also uses radio frequencies, but at a much smaller distance. Their typical implementation is to create what's known as a personal area network, or a PAN, whereby each of our personal devices can be connected to each other to synchronize settings or exchange data. For example, if you have both a smartphone and a tablet running the same operating system, you can use Bluetooth to ensure that the settings of one are replicated to the other, or that a picture taken on one is also replicated to the other. But as a personal area network, Bluetooth intentionally has a range of only around 30 feet to help ensure that your devices aren't easily accessed by other devices, and it also helps to reduce possible interference. Lastly, another common interface type in use these days is known as Near Field Communication, or NFC, which is a very short-range technology, in fact, as little as 4 centimeters or less, used to transfer only small amounts of data between devices. One of the most commonly used applications of NFC these days is the tap payment method for payment cards or mobile phones. You simply tap or touch the device to the payment terminal, and NFC is used to transmit the payment information to the terminal. Because of the secure nature of the payment information, NFC intentionally implements such a close range to help ensure that no other devices pick up on the data. Regardless of the method of communication, though, all types require some kind of interface to facilitate the exchange of information. But that said, almost all types of computing devices in use these days have those interfaces either built in by the manufacturer or available as removable or detachable peripheral devices. So all we need to do is to ensure that our cables are physically connected, or that the appropriate Wi-Fi settings or Bluetooth pairings have been configured, and you're ready to start communicating. In this video, we'll examine several different types of networking devices and the role they provide in facilitating communication among many devices. But just before we get to that, in most of today's networks, there are 2 key concepts that must also be considered: the IP address and what are generally referred to as nodes. For starters, an IP address must be assigned to any device on the network that needs to communicate using TCP/IP, and any device that has an IP address can be regarded as a node. But just for the sake of mentioning it, when TCP/IP is the core network protocol being used, which it almost always is, then you might also hear the term host, which is fine in most cases, but officially, a host is any device with an IP address. A node is any physical device on the network that is able to communicate regardless of the protocol being used. For example, if your laptop is transferring a picture to your phone over a Wi-Fi connection, then they would be using their respective IP addresses, and they can rightly be called hosts. But if that same laptop is synchronizing settings with a phone over Bluetooth, well, Bluetooth doesn't use IP addresses, so they would be regarded as nodes. So, more generally speaking, a node is any physical device that can communicate on the network using any protocol. But as far as most networks are concerned, TCP/IP is usually the protocol in use. Now, another concern that is related to the IP address is what's known as the port. which helps to refine a connection between devices by specifying exactly which type of service or application should be used to satisfy the request. A good analogy of this is if you're staying at a hotel. In order to get to the hotel, you need to know its street address. But once you check in, you're also given a specific room number. Well, in TCP/IP, a similar approach is used. An IP address only identifies a device as a whole on the network, but there are many different applications and services on any given computer. So the port is used to identify which type of service is being requested. Now, you might not be aware of it, but a common example that most of us are likely familiar with is simply opening up a browser and going to a specific web page. You may have seen the letters HTTP in the address line, which stands for Hypertext Transfer Protocol, which at a more basic level specifies a port number of 80. Now, all we have to do is type in something like www.myfavoritewebsite.com, but that name is just an easy-to-remember alias for an actual IP address. So if you knew what the actual IP address was, you could absolutely just type that into the address bar and it would work. But browsers are pre-programmed, so to speak, to include the HTTP in the address so that once the receiving computer is located by its name or its address, the port number of 80 instructs the receiving computer to serve up its web page as opposed to some other service that it's able to perform, such as processing a print job or sending an email. Now, that's only one example. Different applications have their respective port numbers, and they're all pre-programmed in as well, so that when client computers contact their respective servers, the port numbers make the appropriate request. We almost never have to worry about specifying a port number ourselves, but they are required to ensure that the applications we use receive the correct type of information. Another quick example is when you hit send and receive in your email application. The server that receives the request also sees the appropriate port numbers included within that request so that it knows to send us back our email instead of some other type of data such as its intranet page. And of course, when working in a wired network, the type of cable that is being used must also be considered because different types of cables have different capabilities and implementations. For example, in standard client-server networks, you would almost certainly find Ethernet cables being used, but some older types of Ethernet cable aren't as fast as newer types. So while they might physically work, you might not be getting the speed you need. And if you need to connect one building to another on the same university campus, for example, that are more than 100 meters apart, then Ethernet cables can't span that kind of distance, so you might need to go with fiber optic cabling. But with those considerations addressed, the network devices themselves that handle interconnectivity include the modem, which is a contraction of modulator/demodulator. And that modulation and demodulation refers to the conversion of digital computer signals so that they could be sent over traditional analog phone lines. Modems are one of the first ways by which computers could communicate over distances greater than what you would find in a local area network, such as connecting to your internet service provider from your home computer. For the younger viewers out there, you can be thankful that you never had to deal with modems because they literally used your phone line to dial the server of the internet service provider, and they transferred data in a value measured in kilobits per second, whereas high-speed internet these days is measured in gigabits per second. And just to put that into context, 1 megabit per second is 1,000 times faster than 1 kilobit per second. And 1 gigabit per second is 1,000 times faster than 1 megabit per second. Or, to put it another way, 1 gigabit per second is 1 million times faster than 1 kilobit per second. But when I began my career in IT, a 56.6 kilobit per second modem was the standard. Now, more recently, even with high-speed internet, you may still have heard the term modem, such as in cable modem or DSL modem. Those are still modems because they still modulate digital transmissions so that they can be used over analog media, in this case, either your cable TV cable or still your phone lines, but they were at least able to greatly surpass the speed of dial-up, well into the megabit range, in fact, but by today's standards, that's still relatively slow. A router is the device that is required for any data to pass from one network to another, including connecting your home to the internet. With the router in place, you can still create a LAN within your home, but in order for packets to leave your home network and reach that of the internet service provider, they must go through a router. In larger corporate networks, routers are also used to create smaller, more manageable networks, which helps to reduce the amount of traffic on any given network. But the important distinction of a router is that they aren't used to connect individual computers together. They connect networks together and effectively have no knowledge of the individual nodes on any given network. They only see the other routers to which they can connect. An access point is officially any device which can provide you with access to any given network. But in today's implementations, they most commonly refer to wireless networks. One of the most common examples is simply the Wi-Fi network that you likely have in your home. Any device with the correct configuration can connect to that network, but they must connect through the wireless access point. Now, in many cases, that same device is also your router, which provides you with access to the internet, but the access point is solely concerned with the connections between the individual connecting devices and itself. Routing to the internet is provided by a different service. They both just happen to be performed by the same device. A more expanded version of this would be when you connect to a Wi-Fi network in an airport or a hotel. The access points themselves don't provide any connectivity directly to the internet. They just connect the individual devices to the network. But hotels and airports are so large that a single Wi-Fi router just couldn't provide enough coverage or capacity. So when you make a connection in those cases, you connect only to the access points. Then they forward your requests for internet access off to a router. So there might be dozens of access points, but you might still only need a single router. A hub is a device used to connect computers together when using wired connections, and they simply allow all connected devices to communicate with each other as long as they're all physically connected to the hub. Hubs are the effective predecessors to switches, but for lack of a better word, they aren't as smart as switches. So, what distinguishes a switch? Well, for starters, they both provide the same basic functionality in that all devices connected into the same switch will all be able to communicate with each other, but switches are aware of addresses. Hubs are not. In other words, if there are, let's say, 12 computers plugged into a small hub, and computer 1 sends a packet destined for computer 2, all other computers will receive a copy of that packet. Now, they won't do anything with it, but in short, everyone hears what everyone else is saying. So hubs are noisy, so to speak. But as mentioned, switches have additional programming built in that makes them aware of addresses. At this level, specifically what's known as a MAC address, which stands for Media Access Control, also sometimes known as a physical address. But regardless, the address still uniquely identifies each computer that is plugged into the switch. So when that same packet is sent from computer 1 to computer 2, the switch knows which physical cable connection represents computer 2, and it only forwards the packets to computer 2. So all other computers don't hear anything. Hence, switches are much quieter and much more efficient. The term switch itself literally came from the early days of phone lines when an operator had to sit at a switching panel with patch cables and connect an incoming call from one sending physical line to the receiving physical line. The patch cable they connected between the two ends would complete the circuit and communications could begin. The next call would then require them to switch the patch cables to another physical connection, but they still allowed for communication to occur between the intended sender and the receiver only, as opposed to everyone. A bridge is similar to a switch in that it can also filter traffic based on MAC addresses, but they perform a function a little more similar to a router. So the common implementation might be that you already have one network created using a few computers connected to a switch, but you also have another network with other computers connected into a different switch. Now you want to connect those two separate segments together. Now, just for the sake of knowing it, you can absolutely just connect switches together in series, but bridging can simply make that process a little simpler because the bridge is only concerned with each segment or group as a whole. In other words, if computer 1 on segment 1 is sending to computer 2 on the same segment, then the bridge just ignores that packet entirely because the existing switch on segment 1 will forward the packet accordingly, so it doesn't even reach the bridge. But if computer 1 on segment 1 sends a packet to computer 1 on segment 2, then the bridge will forward the packet over to the other side, so to speak, so that each side can communicate with the other when necessary. But if most computers only talk to the other computers on their own segment most of the time, then bridging to the other side is only needed occasionally. So it helps to contain the traffic of each side to its own side, thereby reducing traffic overall. Now, just quickly, that configuration sounds very similar to a router, and in fact, it is similar. But the difference is actually in the terms I've been using. So to clarify, just visualize 8 computers plugged into one switch and another 8 computers plugged into a different switch. If you're going to connect those two separate collections, you could rightly call each of those a network or a segment, but the term depends on the addressing. As mentioned, both switches and bridges operate based on MAC addresses. So if you're going to connect those two collections with a bridge, then the correct term would be segment. If, however, you're going to use a router, then each collection must distinguish itself by using a different network address, hence the term network is appropriate. And networks are only discernible by using IP addresses. In other words, switches and bridges are not aware of IP addresses, but routers are. Now that in itself might cause you to think, well, wait a minute, I'm plugged into a switch and I have an IP address and everything works just fine. Therefore, the switch must know my IP address. But while that might seem like the case, there is actually another protocol included within TCP/IP itself known as ARP, which stands for Address Resolution Protocol, which is used to map or equate a MAC address to an IP address. So TCP/IP can be used in conjunction with switches, but at their core, switches and bridges only communicate using MAC addresses. Then for services that need an IP address, such as routing, ARP is used to equate this MAC address to the IP address. Finally, a gateway is effectively a router, and in fact, if you look at your TCP/IP configuration on any given device, most will refer to your router as your default gateway, because it represents the means to leave your network and connect to another. But gateways have additional programming and functionality to support connecting networks of different types and topologies, and even those that use different protocols. Now, these days, most higher level routers are gateways, but by the strictest definitions, a router would only connect networks of the same type and topology using the same protocol, whereas a gateway does not implement those restrictions. And lastly, a repeater is simply a device that can be used to extend the distance that can be traversed by any type of network media. For example, most Ethernet cables are limited to spanning 100 meters. So if any two devices are separated by a distance greater than that, a repeater can be placed in between them. The repeater receives the incoming signal, then usually amplifies it as long as it can still read all contents, then simply passes that same information along to extend the distance that can be covered. So the types of networking devices that you might need to implement will simply depend on your circumstances, but there is almost always some combination of any or all of them that can meet the needs of any situation. In this video, we'll examine various types of connections that are used by the peripheral devices we attach to our computers, which typically include mice, keyboards, printers or similar multifunction devices, external hard drives, webcams, microphones, and many others. Now, in the earlier days of computers, there were fewer types of devices overall, but almost every category of device had its own specific type of connector. Just as a simple example, when I started my career in IT, a mouse, a keyboard, a printer, and a microphone all had their own specific connector types. Now, all of those devices can use the Universal Serial Bus or USB to connect, meaning that it no longer mattered which device was connected to which physical port. As long as you had enough ports, you could connect any number of devices. USB itself was introduced as a standard connection type in 1996 and was not only able to transfer data between devices, it could also provide power. So, for example, a device that might otherwise require its own dedicated power, it might not be required if you connected it to a USB port. Now, that will depend on the type of device itself and how much power it requires, but it also means that for rechargeable devices, all you need to do to recharge it is plug it into a USB port on your computer. Now, there are several different types of physical connectors that will also vary depending on the type and, in many cases, the size of the device itself. But USB defines the standards of how data and power can be transferred, not the connector types. While that is still fairly standardized, in many cases it's determined by the manufacturers. The most recent physical connector at the time of this recording is USB-C, and it's worth noting that some people might say USB-C when referring to the speed and or the power specifications, and while that might be fine in day-to-day conversation, USB-C only refers to the physical connector, not the transfer specifications. As mentioned, these days any number of devices support USB, including mobile phones, game controllers, fitness monitors, GPS and sporting watches, and many others, again, with any device being able to be plugged into any available port. And on that note, I should also mention that if you don't have enough ports, a single USB connection also supports connecting a USB hub, so that one port can be turned into many, and you can even plug one hub into another hub if necessary. But as for specifications, the current standard of USB, again, at the time of this recording, is USB 4, which defines a data transfer rate of up to 40 gigabits per second, and it also specifies that the Type-C connector is required. FireWire, also known as IEEE 1394, which, by the way, stands for Institute of Electrical and Electronics Engineers, and then the 1394 is simply an ID number for this specification, is a connection standard released in 1995 by Apple, but to clarify, it was IEEE 1394 that defined the overall communication specifications, which were implemented by other companies as well, such as Sony and Texas Instruments, but the term FireWire refers specifically to Apple's implementation of this interface, and it became most commonly recognized by that name. Like USB, it could also transfer both data and power, and at the time of its release, it was largely comparable to USB in terms of specifications, although it did support higher power transfer, which allowed larger devices such as external hard drives to connect without requiring a separate power supply. But since FireWire was Apple's implementation of this interface, you could only use it with an Apple computer. So USB started to gain a much stronger foothold in the marketplace when it was released. Now, FireWire and USB have been engaged in a tug of war in terms of specifications since just about day one, and at any given point in time, one may have been superior to the other until either one released its next iteration. But the initial goals of each interface type were in fact different from the beginning. USB was primarily aimed at being more compatible and less expensive, whereas FireWire was designed to be higher performing and support more demanding devices such as cameras, video capture devices, external hard drives, and many others, but again, in most cases, without requiring separate power. The current standard is FireWire 800, so named for its speed of 800 megabits per second. Thunderbolt is an interface developed by Intel, and it should not be confused with the Lightning cable offered by Apple, especially since Thunderbolt cables use the same USB-C connector as Lightning cables. Like all others mentioned so far, the Thunderbolt interface also transfers both data and power, and the current standard is Thunderbolt 4, which is capable of 40 gigabit per second transfer rates. Now, given all of those choices, as far as we're concerned as consumers, we don't usually have much of a choice in terms of which interfaces will be available on any given device we buy. For example, if you buy a new PC today, you'll likely see support for either USB 4 or Thunderbolt connectors if it has an Intel processor, or both of which would likely use the USB-C connector. But you would still likely see the predecessor to the USB-C connector, which is the Type A connector, which is the flat, more rectangular type for backward compatibility. If, however, you're buying a Mac, you'll likely find FireWire and Lightning connectors, which also use the USB-C type connector, and possibly still the USB-A type connector, but that might be more likely if you're buying something used. In any case, as mentioned, we really don't have a choice as to which interfaces the manufacturers are going to include, so we just have to make sure that the devices we want to use are compatible with the interfaces, and if they aren't, then there are usually adapters that can be purchased, but they might sacrifice some performance characteristics for the sake of compatibility. Now, all of those previous interfaces used wired connections, but of course, that's not the only way to connect a peripheral device. Bluetooth is a technology that can connect a multitude of devices over short ranges, usually up to about 30 feet, using radio frequencies in the 2.4 gigahertz transmission band, which, by the way, is the same band used by some Wi-Fi communications, although its low power state and short range generally produces little, if any, interference. And currently there are two versions, Bluetooth Classic and LE, which stands for low energy, but that doesn't refer to the transmission strength, rather the power consumption and or requirements of the device itself. But as a newer implementation, it also has improved capabilities to detect the presence, range, and even the direction of other devices, which can be particularly useful for setting up smart home devices, among other things. Ultimately, the ability to connect a peripheral device to your computer simply comes down to what type of interfaces are available on the computer itself, so you will always need to ensure that you have an interface that is appropriate to the device that you're trying to connect, but as long as it does, then there is virtually no configuration required, at least in terms of configuring the interface itself. In almost every case, you can simply physically plug it in or pair it if it's using Bluetooth and begin using it right away. In this presentation, we'll provide an overview of the various types of display interfaces which determine the overall capabilities of what we as users see on the screen, of course, but also the performance characteristics such as the quality and clarity of photographs, the color depth, how smoothly video files play, and how well your gaming experience looks. Now, effectively, the first standard that was able to produce anything beyond black and white and or a few basic colors was the Video Graphics Array Specification, or VGA. This was an early standard for displays that supported a maximum screen resolution of 640 pixels wide by 480 pixels high. And pixel, by the way, is a contraction of picture element. And it also supported a color depth of 4 bits per pixel, meaning it could display 2 to the power of 4 for a total of 16 available colors. However, if you reduce the resolution to approximately half, in this case 320 by 200, then it could support 8 bits per pixel, or 2 to the power of 8 for 256 colors. Now, by today's standards, that is a very basic resolution with minimal capabilities, but you might still see it in use for some older devices such as PDAs or GPS devices. But like almost any other interface or technology, VGA did develop later versions with higher capabilities known as SVGA or Super VGA, and it supported up to 1280 by 1024 resolution with 24-bit color, which offers millions of colors, and it even meets the specs required by any high-definition output, but all VGA specifications used analog data transfers and a physical 15-pin connector that is starting to become out of date on many devices. In fact, most newer monitors or TVs that you would purchase today would likely not include a VGA connector. Toward that end, newer graphic device interfaces started to appear, including the Digital Visual Interface, or DVI. Now, this is still an older interface by today's standards, but it provided a purely digital output option. But since it was the immediate successor to VGA, it also retained backward compatibility with VGA by providing analog options. Hence, DVI connections were indicated as either DVI-A, which only used analog signals, or DVI-D, which only used digital, or DVI-I, where the second I stands for integrated, meaning that it supported both. Both VGA and DVI were succeeded, however, by the high-definition multimedia interface, or better known as HDMI. Most notably, HDMI, as indicated by the term multimedia in its name, is able to carry both video and audio data. And while the video data is uncompressed, which by the way is the case in all previous methods, the audio could be either compressed or uncompressed depending on the application and/or format. HDMI was initially introduced in late 2003, but it remains a standard for high-definition video and audio to this day. And while just about any computer monitor will have an HDMI port available, you'll also find them on TVs, DVD players, PVRs, projectors, and just about any other type of device that connects to any kind of display, so they're very commonly used. DisplayPort, or simply DP, is the newest display interface, primarily used with computer monitors at the time of this recording, so it isn't quite as widespread in terms of being found on different types of devices as is HDMI, but it does support higher resolution and data transfer rates. Like HDMI, it can also carry both video and audio data, as well as USB data. So if, for example, your monitor is connected to your computer with a standard DP cable, the monitor itself could have USB ports in it, so you could plug any USB device directly into the monitor, and they would work. Now, monitors with USB ports have been around for a while, but they required a separate USB cable to be connected to your computer, in addition to the video connection, so that your monitor could effectively act as a USB hub. But with DisplayPort, that extra USB cable isn't necessary. And this is due to the fact that DisplayPort is the first video interface that uses packetized data transmissions, which is also used in Ethernet networking and USB connections. But it allows for increased performance over its predecessors because they all implement a clock signal in addition to the data, which allows devices to synchronize the data stream, but the packets used by DisplayPort embed the clock data within the packets themselves, so no separate clock signal is needed. In addition, DisplayPort and its improved data transmission methods allow you to connect up to 4 monitors to a single display output on your computer by daisy chaining from one monitor to the next, which is not supported by any other interface type. In order to have multiple displays with HDMI, your computer must have multiple outputs, or perhaps you could use some kind of a port replicator to provide an extra output, but you must have multiple outputs. Lastly, DisplayPort also offers a mini version, which was introduced by Apple in 2008, but the use of the term mini in its name does not refer to the size of the screen, which is a common misunderstanding that I've encountered on many occasions, because of course Apple has the iPad, iPhone, and iPod and other devices, all of which have comparatively small screens. So mini in this context simply refers to the smaller connector on the cable. However, by 2016, mini DP was phased out in favor of the more compatible USB-C connector. Again, like peripheral devices, we as consumers don't really have any input when it comes to which interfaces are going to be built into any given device, but of course it is up to us to choose the interface we want. But it's also worth mentioning that many display devices these days come equipped with both HDMI and DP, so you'll often have a choice in that regard, but of course a display device of any type must also be connected to the video output source, whether that's your computer, a DVD player, or a PVR, or anything else. So, of course, both devices must support the same type of interface. In this video, we'll provide an overview of some of the typical computer peripheral devices and their general setup requirements. And these days, when it comes to installing any type of peripheral device, there is a process that has been around for quite some time, actually, known as plug and play, which means that the operating system comes pre-configured with a repository of commonly used drivers. Now, just quickly, the driver is the piece of software that provides the instructions for how the operating system can access and interact with any given device. So prior to plug and play, the process was to manually configure the driver on your own. Now, I'll actually show you an example of that in an upcoming demonstration, but as mentioned, plug and play effectively means that the operating system already has the driver, and therefore, once the device is physically connected, the operating system recognizes it and installs the appropriate driver automatically. Now, as mentioned, plug and play has been around for quite some time. In Windows systems, for example, it was actually introduced with Windows 95. But it has significantly improved in more recent years, and in most cases, when you attach any given device, it is quite likely that the operating system will recognize it and will install the driver appropriately. But it's certainly not guaranteed to work, so there will still be instances where you will have to manually supply the driver. Now, many devices that you purchase will come with the driver. For example, you'll receive a CD or a DVD with the device, and you simply install that. Then you physically connect the device, and of course, since you have already installed the driver, then the operating system recognizes it, and plug and play will once again configure the device appropriately. But another method by which you can obtain the driver is to simply download them from the manufacturer's website. And in fact, this is the recommended approach, even if the software is included. And the reason why is because drivers tend to be updated like anything else in computing. So even if you do go to the store and you purchase a device and it comes with a driver on something like a CD, that driver might have been written to that CD months ago. So it could have been updated since then. So if you go to the manufacturer's website, you can find the most up-to-date driver, and you can download that and simply use that driver instead. Now, as for some of the actual devices themselves that are commonly installed, they might include printers or scanners, or these days, perhaps more commonly, multifunction devices that can do both printing and scanning, and they might also copy and or fax. But it's still the same type of physical device. And these are one of the more common devices that do need to be installed. There is typically specific software that goes along with the printer or scanner so that you can configure it and interact with it. But as far as just functionality is concerned, really it is just the driver that's required. So for example, when you buy a printer, it might come with additional software that you just aren't concerned with, such as perhaps a photo editor or something that allows you to create more customized print jobs, such as greeting cards. So in many cases, those applications just might not be needed, but the driver is absolutely required. But they might also give you the option to install just the driver. If, for example, you install the software, you could choose something like a custom installation, and then you might see a list of items that can be installed, and you simply choose the ones you want. But in those cases, the driver is something that would always be installed. But if you go to the manufacturer's website, you might find an option to download just the driver. So that can sometimes save you a bit of time, and it would just be a simpler process. Other peripheral devices include keyboards and mice. Now, with respect to both of these devices, in almost every case, the computer will detect those and install and configure any necessary drivers automatically. But there are still certain cases where software does come with the keyboard and or the mouse, simply because there might be configurable options for those devices. For example, a keyboard might have some custom keys that you can configure to perform your own specific actions. Mice, of course, are very simple devices, but gaming mice in particular also have multiple buttons that can be pre-programmed with certain actions. So there might be this configuration software, but it would be optional. As far as functionality is concerned, the keys of the keyboard would work and the mouse would move your pointer around automatically in almost every case. Other devices might include a camera, and once again, the ability to simply transfer photos from the camera to the computer is probably going to work right away. In other words, plug and play will handle that. But similar to the printer, the camera might come with additional software. Again, a photo editing application is a good example. So that would be optional, but the functionality of transferring the data is probably going to work straight away. And the same really goes for an external hard drive. In almost every case, as soon as you plug it in, it will function. But once again, there might be software that allows you to configure something like an automated backup process by simply pressing a button on the device. That would also be optional. As far as functionality is concerned, almost every operating system will detect the external hard drive right away, and it will install any necessary drivers automatically. Speaker connections typically do not involve any additional software, again, with respect to functionality. The most common type of connection for speakers is probably still what's known as a mini jack. It's also the same connection that you might see on a set of headphones, but that's certainly not the only option these days. You can also connect speakers using an HDMI cable because that does carry audio. And you might also see what's referred to as an SPDIF, which stands for Sony Philips Digital Interface, which is a type of coaxial connection. But again, the mini jack is still by far the most common, and there is almost never a driver required for speakers. You just plug them in and they work. Yet again, there might be some type of software that is included with the speakers, some type of audio mixer application, for example, but that would be optional. In terms of functionality, they would almost certainly work straight out of the box. Lastly, display connections include VGA and or DVI, HDMI, DisplayPort, and the ability to use any or all of those with multiple displays. Now, I'll come back to that in just a moment. But as far as the interface goes, these days, HDMI and DisplayPort are the current standards, but on older systems, you might still find VGA and or DVI. Now, when it comes to configuring and or installing the monitor, this is yet another example of a device that almost never requires any type of driver or configuration just for functionality. But as has been the case with almost everything else we've talked about, there might still be software included with the monitor that allows you to create customized display options or different configurations. But as soon as you plug them in, they almost always work straight out of the box. So typically, no drivers are required, at least nothing that you have to configure manually. Now, just to finish up, quickly going back to multiple displays, any given computer can certainly support multiple displays, but if you are using any of VGA, DVI, or HDMI, the computer itself must have multiple outputs. So any single screen can only be connected to a single output device. Now, on a desktop system, you can certainly purchase a video card that would have multiple outputs, but you do still need one per screen. On a laptop, you have the built-in screen, and then you very likely would have some additional outputs, such as HDMI, so that you can connect a secondary monitor. But DisplayPort allows you to connect up to 4 displays using only a single output. They can be daisy-chained together. So it's going to depend on the configuration of your system with respect to using multiple displays, but once again, there are typically no drivers required to implement those types of configurations. So overall, when it comes to most peripheral devices these days, you'll want to rely on plug and play. It is a simple process, and it has been improving over time so that most devices are detected and installed automatically. You might still implement your own particular configuration, but the device will function with little to no user interaction required. In this presentation, we'll provide an overview of the various types of peripheral device installations that can be performed on a computer, along with some of their basic characteristics and attributes to help you determine which method might be the most appropriate to use in any given situation. Now, the first consideration with any peripheral device is to ensure that your system meets the minimum requirements of the device itself, most notably the minimum version of the operating system that supports that device and/or any other hardware requirements. Now, just quickly, things like the amount of RAM or the processor specifications usually aren't that much of a concern when it comes to peripheral devices, but certain types of devices might simply require the presence of other components. For example, some security-based devices such as fingerprint readers, retinal scanners, or perhaps an infrared camera for facial recognition might require the presence of what's known as a trusted platform module chip, which is a chip embedded directly in the motherboard, which can securely store data in an encrypted format to help ensure the safety of the data it contains. But that will depend on the nature of what you're installing. You should also verify the version of the software and/or drivers being installed, even if the device came with pre-packaged software, because that software may have been written months ago, so there might have been an update since that time. Now, you can typically verify the latest version by going directly to the manufacturer's website and searching for the same software or driver package, then compare the online version with what's written on the disk that was included. In some cases, the version might still be the same, but a bug or a glitch might have been discovered with the original version, in which case an update or a patch might be available. In those cases, you can still install from the included disk or from the downloaded version. It wouldn't really matter if the version is still the same in both cases, but then you would apply the patch afterward to address that issue. And once the installation has completed, there might also be a configuration interface that was included with the software, or in many cases, you can also just use the inherent interfaces of the operating system, such as the Device Manager utility in Windows, the Settings app, or the Control Panel. For example, if the device you just installed was a new wireless network adapter, you might have to configure it to the appropriate security settings and/or transmission band to connect to your Wi-Fi. Another consideration might be to ensure that you're using authentic, or what's also known as signed drivers. Now, if you're using the driver that was either included with the device itself or you've downloaded it from the manufacturer's website, then it will most certainly be authentic. But there are sites available online where more generic drivers can be downloaded. And they might very well work, but they would not be the authentic driver from the manufacturer. And as such, they might result in some instability or reliability issues. And a signed driver is one that has been vetted and approved by the manufacturer of the operating system onto which those drivers are being installed. One of the more common examples of this is Microsoft Windows, particularly 64-bit instances of Windows, which require the use of signed drivers. Signed drivers are ideal, of course, because if they have been approved by Microsoft in this example, then it also means that they're almost guaranteed to work. And I only say almost here just to allow for things like possible corruption in any of the files. But the potential issue that can arise is that device manufacturers themselves have to pay to have their drivers signed by Microsoft. So some might not want to do that. Although almost any reputable device manufacturer will, because it will in turn boost sales and improve device reliability. In any case, while signed drivers are required on 64-bit versions of Windows, you might still be supporting older systems that are only running 32-bit versions, which don't require signed drivers. So you might be able to successfully use one of the more generic versions mentioned earlier, but ideally, signed drivers should always be used. Also required for device installation are the correct user rights, permissions, and access level. And in short, you usually need to be using an account that is at least an administrative or a supervisory account, at least on that local device. Now, I say that local device because if you're operating in a networked environment, then there are also administrative level users for the entire network, in which case they're also administrative on most other devices. But you can be just an administrator of your own local device without being a network level administrator. And this is also often required just to perform some device configuration tasks, such as updating a driver. Now, that will depend on the device and the operation you're trying to perform. For instance, you would likely need to be at least a local administrator to update the driver for a printer, but you would not need that kind of access just to reconfigure the device to print in black and white as opposed to color. That would be an example of a user preference, so you would not need to be an administrator in that case. As for the typical installation methods for peripheral devices, the most common method is referred to as plug and play, whereby you physically install or connect the device itself. Then the operating system automatically detects its presence, identifies its type, make, and model, and installs all necessary drivers on its own. In other words, you literally don't have to do anything. Now, plug and play actually comes back to the topic of signed drivers, because not only are the drivers verified by the operating system vendor, they're also preloaded into the operating system so that devices can be recognized. So this, again, is why you should always try to use a signed driver. If the operating system has a preloaded copy, then plug and play should work in almost every instance. That said, the drivers that are provided might still possibly become outdated if the manufacturer has released several new versions since the initial version was included with the operating system, or the device itself might have been updated to the point where the pre-provided driver is no longer the correct version. So there will very likely be instances where you still need to provide the driver manually. In such cases, the recommended approach is to still go directly to the manufacturer's website and locate the most recent version of the driver that is appropriate to the device itself and simply download it to your computer. Most downloads will include either a self-installing executable, which installs all necessary drivers and components on its own, or it might have a self-extracting file which unpacks the driver files into a folder. Then you can usually use the property page of the device itself, which typically has a driver option, whereby you can specify the location of the new driver. So whether you're installing a new device or updating the driver for an existing one, the general approach is to ensure the device itself has power, if applicable. And I say if applicable because something like a printer obviously must have power, but something like a sound card draws its power directly from the motherboard, in which case you just need to make sure that it's fully inserted and or connected if perhaps it's an external device such as a webcam. Then install the driver and or provide the location as just discussed, then configure it accordingly once it appears to have been correctly installed. Now, that said, I do just want to finish up with a little bit of a caveat. This process might actually work more reliably in some cases if you reverse steps 1 and 2. And the most common example of that is when you're installing printers. In other words, if you have just purchased a new printer, then step 1 is typically to launch the software installation first. You can have the printer itself fully in place and ready to go, and even connected with both power and a USB cable, if that's how it's going to be configured, but leave the power turned off. In most installations, the install process itself will apply the appropriate drivers first. Then it will actually inform you to plug in or turn on the printer at the appropriate time. Since the installation process has already applied the drivers, the operating system will detect the new device as soon as you power it up, and it will invoke the plug-and-play process, which in turn will locate that driver that was just installed and correctly complete the installation. Now, again, that's just one example. For something like a sound card or any other internal device, you would normally follow the steps listed here because you have to shut down the computer entirely and open it up to physically install the card. But once the system reboots, it should again detect the presence of the new device, and in most cases, plug and play will complete the installation automatically. But if it doesn't, then you can install the manufacturer-supplied software at that time, and it should complete the process accordingly so that you can begin using that device. In this demonstration, we'll take a look at performing basic device configuration. Now, this process is going to vary depending on the device you're working with and, of course, the operating system you're working with, but the general process should be the same in most cases. Now, I'm actually going to work with an existing device here, and I'll show you the process of updating the driver. But this approach would also apply even if I was just installing the device new, out of the box, so to speak. So in this case, I'm going to work with my wireless network adapter. So even though I already have the device installed, and as mentioned, I'll show you the process of updating the driver, the steps would largely be the same even if I just physically attached this device. Let's say, for example, that it was an external wireless adapter that was just connected to a USB port. If I simply physically connected it, then rebooted my computer, plug and play probably will detect it, but it might not install the correct driver, in which case you would probably still see the device listed in the Device Manager utility. And I should have clarified that actually I am working on a Windows 10 system, and this utility is known as the Device Manager, which of course allows you to manage your hardware devices. And you can access this utility by simply right-clicking on the Start button and then choosing Device Manager. Okay, so that's where I'm at right now. And again, I already have this network adapter installed, and in fact, I will tell you that it is using the most up-to-date driver, but we can still go through the process. And as mentioned, even if I had just purchased this device and physically connected it, and it did not correctly install the appropriate driver, then the process is still the same to supply the correct one. So in an earlier presentation, we talked about obtaining drivers, and in most cases, when you purchase a device, it's quite likely that it will come with its own software on a CD or a DVD. But in fact, I'm working on a relatively new laptop that does not have an optical drive installed. So I would not even have the ability to install from a disk. So really my best option is to download the driver from the manufacturer's website. So I do have that site up here. Just let me switch over to my browser. And I started with just a general internet search for the specific make and model. And then I simply ensured that I was searching for the driver for this model. So there's my search bar right there. And that brought me to this result down here. And you might notice that there are, in fact, two options here, one from the Intel site and one from Dell. This particular system is a Dell, so I went to this result right here, and that is this page, okay? So I can just scroll down a little bit, and what you see here is an option to download the software package for this particular device. So I have already done that, and it simply went into my downloads directory. So let me minimize here, and I have that folder open as well, and here is the actual file that was downloaded. Now I can still go through this process. I'll just double click on this file here. So now there are two choices. You can simply click on the install option or extract the contents. Now that's up to you. The install option will likely present you with all of the available software that can be installed, including the driver. And this might also be an example of what was mentioned in an earlier presentation, whereby there might be some additional software that really isn't required. Now, again, that's not a big deal. You can certainly install it, but for something like a wireless adapter, there's a reasonable chance that it might install some management or configuration software that certainly would function, but it just might not be necessary. my Windows operating system is fully capable of managing the device itself. So again, that's your call. But with respect to what's required, that's where the driver comes in. So in this case, what I can do is to simply extract the contents of the executable, and that's the option I went with. And look what it did. I told it to simply extract everything to my desktop. So there's the setup.exe, which would be the same as installing it, but the extraction created a drivers folder for me, and this contains the drivers that are necessary for my particular operating system, which is Windows 10. So this folder contains the drivers that I need. Okay, so I have them here on my desktop. So the process for updating or even just installing the appropriate driver is going to be the same in either case. We can now just return back to the device manager. And since mine is already installed, I can just choose the update process. But again, had I just physically installed this and the correct driver was not installed, then this process is still applicable. So what we can do is to right-click on the device and we can choose to update the driver. Now you can also just double-click and you can go to the driver tab, and there is an update driver option as well. So we just click here. Now you can have Windows search automatically for drivers, but that might take a little bit of time. I can just browse for the drivers because I know where they are. I placed them here on my desktop. So I'm going to go with this option to browse. Then I can just click on the Browse button, choose the desktop directory, drill down to the drivers folder. Then I can specify this Windows 10 directory and click on OK. That puts the entire path here, and notice that there is a checkbox to include all of the subfolders because there are some different iterations and or makes and models of this particular driver. So this will search all of them for the most appropriate driver. So it's a good idea to have that checked, but do make sure that you choose the appropriate operating system. We'll click on Next, and it's going to go through and do a check. And as mentioned, mine is already using the most up-to-date driver, so it's telling me that Windows has determined that the best driver for this device is already installed. Okay, but if this was a new device, it would simply present me with the list. I would see the Killer Wireless 1535 network adapter available as an option. I would simply click on that, choose Next or Apply, and that's it. It would install the drivers that are in that folder, and the device would be properly configured. Okay, so again, the general steps are to physically install or attach the device, download the appropriate drivers, ideally from the manufacturer's website, and simply store them in an accessible location. If there's an installation option, you can absolutely go that route and simply choose to install the drivers and then optionally choose to install any other software that it might include. Again, that's your call, but as far as functionality is concerned, the only thing that's required is the driver. So in that case, you can often choose to simply extract just the driver and again, place it in a folder that is accessible, then go into your device manager, choose to update the driver, and simply direct the operating system to look in the appropriate folder to locate the necessary drivers. It might require a reboot after that depending on the device, but in most cases it will start functioning right away. If you do need to reboot, just make sure you close and save any other work that might be in progress, and once your system comes back up again, you can go back into the device manager to verify that it has installed correctly. In this presentation, we'll take a look at computer motherboards and the role they play in computing, which in short is the role of all roles, because the motherboard is the primary circuit board of the entire computer itself, into which all other devices connect or attach. In short, without a motherboard, you have a rather useless collection of hardware. Now, while many other components of a computer are certainly critical to providing functionality, again, without a motherboard to house them, none of them could do anything. So I've often referred to the central processing unit, or the CPU of a computer, as its brain, so to speak. And as such, without it, the computer would also be just about useless. But if the CPU can be thought of as the brain, then the motherboard can be thought of as the central nervous system because it provides the means not only for the CPU to function, but for its instructions to be communicated to all other components in the system. For example, in order for the CPU to write the results of a calculation to the system memory, there must be a communication pathway between the CPU and the memory, and that pathway resides on the motherboard. So some of the common physical components that you can expect to find on a motherboard include a socket to hold the CPU, slots to hold the memory chips, a power connector that comes from the primary power supply, which in turn distributes power to all internal devices, a chip that contains the basic input-output system, or BIOS, which provides users with an interface to configure the components of the motherboard and other basic devices. We'll talk about the BIOS in greater detail in an upcoming presentation. A battery backup that provides power to the BIOS chip to ensure that its settings are retained when there is no primary power. Various chipsets that perform any number of support operations, storage interfaces for hard drives, optical drives, and/or solid-state drives, cooling fans, slots for peripheral or expansion cards such as video or sound cards, and external device connectors such as USB ports. Now, for better or worse, various computer manufacturers design and build computers of different physical shapes and sizes, so there is no one-size-fits-all option when it comes to motherboards. But there are at least some standardized implementations that are observed so that not every single motherboard is a custom-designed, unique instance. And these standardized versions are referred to as the form factor, which quite literally defines the physical dimensions and the placement of all those components we just listed, but it effectively determines the overall size of the entire computer itself. Now, one thing you'll notice about every entry here is that they all end with the letter X, which in every case stands for extended. So, for the very first entry of ATX, this form factor was developed by Intel, and it was an extension of the original AT design by IBM, where AT stands for Advanced Technology. Now, that said, the AT form factor goes back decades, so it was advanced at the time, but in any case, ATX then stands for Advanced Technology Extended, which makes the second entry seem rather redundant because that would literally read as Extended Advanced Technology Extended. But the original X, to indicate extended, meant an extension to the technology itself, whereas the first extended in this entry refers to a physical increase in the size of the motherboard. It's meant to be used in full tower cases with a lot of space for expansion so that more powerful systems could be assembled and leave more breathing room, so to speak, to ensure adequate air movement and cooling. Now, those form factors are popular with enthusiasts, gamers, and special use systems, but of course they take up a lot more space. So for situations where space might be more limited, as their names indicate, the mini and micro version of ATX are much smaller. And while micro is often the prefix used for the smallest of any given item, in fact, in this case, mini is smaller than micro. For comparison, the original ATX measured 12 inches by 9.6 inches. Extended ATX is 12 by 13. Micro is 9.6 by 9.6. And mini is 6.7 by 6.7. Like any technology, however, improvements are inevitable, so the BTX was introduced as the successor to ATX around 2005. And it similarly offered varying sizes, including the original and micro, along with some later variations as well. And then ITX came along, not so much as a successor to BTX, rather to create a more specific form factor to accommodate lower power and less expandable systems that are commonly found when only a small space is available to house them, or in special use systems such as kiosks or digital signage. Now, as far as choosing a form factor goes, that is of course up to you, but you should certainly consider its purpose and use and how much physical space you have. As mentioned, enthusiasts and gamers typically want their systems to be as large as possible, to accommodate more devices and better cooling. But corporations likely have limited space per office or per cubicle, and the systems they use would not need the performance characteristics of a gaming system. So choosing a motherboard and its associated form factor is always going to be dependent on the circumstances. As for the actual components that connect to a motherboard, they include the CPU chip itself, the random access memory or RAM chips, the graphics processing unit or GPU, which might be in the form of an embedded chip right on the motherboard, or an expansion card, which is generally referred to as a video card, hard drives and or solid state drives, optical drives, which are the CD or DVD drives, and sound cards, which, like video cards, might also be in the form of embedded or built-in chips or a separate expansion card. And on that note, I should mention that components such as video and sound are often built into most motherboards these days, and they would certainly function adequately for most users. But if, for example, you were building a system specifically for recording music or for gaming enthusiasts, those built-in components would never be adequate for those tasks. So separate and dedicated cards are installed to handle the more demanding requirements for those types of systems. As the primary component of your system, you'll need to be mindful of things that could cause damage to your motherboard, including excessive heat, which comes back to the larger systems used by enthusiasts and gamers. Because they often use those dedicated cards that perform at much higher levels than the built-in components, they also generate much more heat. So systems such as those will often have several fans in the case to keep air circulating and the heat from building up. Many internal computer components would overheat in a matter of minutes if they weren't properly cooled, to the point where they could easily burn to the touch or even melt or burn other components on the motherboard itself. Despite the heat levels that can be reached, most computer components operate at very low power levels, so they're quite susceptible to power surges. So ideally, your system should be plugged into a surge protecting power bar or other type of power conditioning unit. And the circuit pathways themselves are just very thin layers of metal, so any direct impact could easily damage the motherboard. So be especially careful not to drop anything on the board when servicing your system. And incorrectly attached cables and connectors can also cause damage, especially if any kind of power connector is incorrectly attached. Now, these days, most connectors are keyed so that they can't be incorrectly attached, but it's still possible in some cases, particularly on older devices. Some final considerations include general maintenance and upkeep, which might include upgrading the BIOS, which I will tell you is not something that is overly common, but it certainly can be done if the manufacturer releases a newer version, which might have been released to correct a newly discovered issue or to simply upgrade the capabilities. But before doing so, you absolutely need to verify the make and model, because applying an incorrect upgrade to a BIOS can damage it permanently. Now, ideally, if you have the original product documentation, then that will certainly tell you the correct make and model, but you can usually obtain that information from the board itself. Model numbers are typically written or inscribed directly onto the board somewhere. Or if you're running Windows as your operating system, you can launch a command prompt and use the WMIC baseboard command to retrieve the make and model. If you suspect your motherboard needs to be replaced, you can do so. And while it's not a terribly complicated operation to perform on a desktop computer, it's notably more difficult on a laptop, not only due to the limited space, but almost everything in a laptop is integrated into the motherboard, so it's almost never worth the cost. In other words, it would just be cheaper to buy a new laptop. Even with a desktop, while it might be easier and more cost-effective to replace just the motherboard, depending on the system's age, you might not be able to use your existing processor, memory, or expansion cards on the newly purchased board. So you might end up having to replace all of those components as well, which might also make it less expensive to just buy an entirely new system. As for checking to see if your motherboard is dead, clearly no activity whatsoever when you power up the system could be indicative of a problem with the motherboard, but it could also be a problem with the power supply, so that's not an immediate indication. But if it's not quite dead, but seems to be on its last leg, so to speak, you might encounter some activity, but then it might quickly shut down again and just keep cycling. Or you might also smell burning if the problem is related to overheating. And one very noticeable giveaway is often a chemical smell and or visible corrosion on the small capacitors on the board. If you've ever seen a regular battery corrode, this would look very similar. It appears as a white, powdery but crusted substance on the top of the capacitors. And the capacitors themselves, by the way, resemble small batteries. But if you're seeing that corrosion, even if the system still boots, it will almost certainly fail soon. If you don't feel like you're capable of replacing the motherboard yourself, any local technology store should be able to, but again, be sure to get an estimate on the cost before proceeding. Since the motherboard is the main component of your computer, again, in some cases, buying an entirely new system might be less expensive. In this video, we'll take a look at what's known as firmware and the basic input-output system, or BIOS, of a computer, along with their implementations and the role they play. Now, to begin, the term firmware is meant to refer to some kind of middle ground, so to speak, between hardware and software. But to clarify, firmware is still software, but it's a very specific class of software that provides low-level device control and configuration. So, fine, what does that all mean? Well, for starters, if we think about what most of us might consider to be regular software, such as a web browser, a word processor, or a spreadsheet, those applications are essentially portable in that they can be installed on just about any computer, and they offer a wide variety of features and configuration options to suit each user and their particular preferences. And they're very frequently updated with new features and new versions. Firmware, however, is not portable. It doesn't get installed on a variety of computers, and it offers very little in terms of configurable options. And while it can be updated, changes are usually infrequent and minimal in terms of size. But more to the point, firmware contains the specific program code and data for a specific piece of hardware, and only that piece of hardware. Now, just quickly, when I say only that piece of hardware, that doesn't mean a single unique instance, but it does refer to each instance that would be of the same make and model. For example, every printer of model ABC by manufacturer XYZ would have the same firmware. And the low-level device control refers to the basic instructions for that device to be able to provide its core functionality. And in that regard, that does not mean interacting with your computer. But if you think about something like a printer, for example, in order for it to function with your computer, you also have to install a driver. And that would be a higher level instruction set so that the computer is effectively able to send instructions to the printer, such as to print a document. But there are different drivers for different operating systems. For example, one for Windows and one for Mac. But there would still only be a single instance of the firmware for that printer. So the driver would submit something like the print command to the device, but the firmware would instruct the device itself as to how to position the print head, feed the paper, and correctly time the sprays of the ink itself. So that's what's meant by the very low-level device control, the core functionality of that device. So since it's specific to just that device, and it generally is fairly static in nature, the term firmware was applied. So one of the most common examples of firmware is the basic input-output system, or BIOS, which is the firmware for personal computers. Recall that it is still software, but in the case of a computer, it is not something that is installed on the hard drive like a standard user application. The BIOS is contained within a dedicated chip that is permanently affixed directly to the motherboard. So regardless of which operating system gets installed, the BIOS remains the same. And it's always the first software that processes whenever the computer is powered up. And at that point, it's not even aware of which operating system is installed. nor does it care, for lack of a better word, because it's only concerned with that very low-level device configuration and operation, such as CPU and memory functionality. Now, as of the time of this recording, there are two primary types of BIOS and/or firmware. Legacy BIOS is typically found on older motherboards, but it would certainly still be in use today on some systems. And while BIOS itself is a fairly generic term, manufacturers of motherboards were entirely free to create their own bespoke implementations of BIOS. But there are some basic architectural limitations to the framework itself, so to speak. For instance, BIOS-based computers are limited to data storage drives of 2.1 terabytes at the time of this recording. So anything larger than that is simply not recognized. And even that is a major advance since the early days of BIOS. When I began my career in IT, the largest drive supported by any BIOS was 512 megabytes. Now, that's only one example, but again, the core architecture of BIOS imposes several limitations that are simply being surpassed by newer technologies. Hence, the Unified Extensible Firmware Interface, or UEFI, was introduced as the successor to BIOS. Not only does it accommodate the newer technologies that aren't supported by BIOS, even the interface itself is much more functional. The BIOS interface is often only navigable using arrow keys on your keyboard to browse through menu options, whereas UEFI provides mouse functionality, and some UEFI interfaces are even able to use the network interface to directly download updates from the manufacturer's web services, whereas with BIOS, upgrades have to be downloaded separately and stored on something like a flash drive to be applied. As for some key functions, when the computer is first powered up, a basic diagnostic routine known as the power on self-test or POST is initiated, which tests for the presence of the core components such as the CPU, memory, and storage devices. BIOS drivers are then loaded, which, very much like operating system drivers, instruct your hardware devices in terms of their basic functionality. But at this level, hardware devices refers to the core components that are embedded directly onto the motherboard, not something like a printer driver. Then the BIOS setup will apply some basic configurations such as the current time and date, and any passwords that have been configured for allowing access to the BIOS interface, and any settings that are user configurable. For example, the boot sequence can be altered so that instead of booting into the operating system from the locally installed hard drive, you might choose to boot from the DVD drive if you're installing a new operating system or performing maintenance on the current one. And finally, the bootstrap loader attempts to locate a compatible operating system on the device from which it is configured to boot, and if found, it will pass control of the boot sequence onto that operating system, at which point the BIOS level processes are complete. As for accessing the interface itself so that you can make configuration changes, it varies depending on the manufacturer, but it almost always involves pressing a specific key or perhaps a keystroke combination immediately after the power has been turned on. Now, it really can be any key, but common examples include the delete key or the F2 key. But some systems will tell you which key to press during the boot process and even when to press it. But for security reasons, some systems will not display that information. But that might also be an example of a user configurable value. For example, there might be an option within the interface to enable and/or disable that message, informing you of which key to press. But if that message is off by default, then you'll have to access the product documentation to find out which key it is. But this would also be likely easy discernible through a standard internet search, provided you know the specific make and model of your motherboard and/or device. For example, if it's a proprietary device such as an HP or a Dell, you might not know the specific motherboard that is installed, but if you search based on the make and model of the computer itself, you should be able to find out fairly easily. Lastly, some examples of configurable options in the BIOS interface include modifying the boot sequence, which was already mentioned, but again, this is used to tell the system to search for an operating system in a specific order. And while it's most commonly set to look on the locally installed hard drive, other options include a DVD drive, a USB flash drive, and even the network interface. Now, all options other than the local hard drive are typically only used when installing a new operating system or performing maintenance. But that's an important option, especially when you are trying to install a new operating system. For example, if you just assembled a brand new system for the first time and the hard drive is entirely empty, and this, by the way, is also referred to as a bare metal system, and now you're trying to install a new operating system from DVD, then if your BIOS is configured to look on the hard drive first, then it won't find any operating system because, of course, that drive is empty. And it might simply halt the boot process at that point and not allow you to proceed any further. So you have to get into the BIOS to make sure that the DVD is first in the order. The installation DVDs for operating systems do contain minimal operating system environments so that you can invoke the installation. In Windows, this is referred to as the pre-install environment. So this again provides you with the ability to be able to install the operating system from the DVD. In order to update, or what's often referred to as flashing the BIOS, you generally have to begin in the BIOS interface so that you can direct it to the source of the update. Various devices can usually be enabled or disabled depending on whether they're being used. For example, if you have installed your own sound card, you might not use the built-in audio at all, so it could be disabled. Some systems might allow you to adjust the clock speeds for the CPU and memory, and there are usually some monitoring options such as viewing the current CPU temperature and adjusting the CPU fan speed if perhaps you feel like the CPU might be running too hot, or there might also be a configurable alert whereby a beep or an alarm might sound if the temperature exceeds a configurable threshold. So again, while there are some user configurable values, the core code of the BIOS itself is set, and it's specific to that make and model of the motherboard. And if updated, it's only done infrequently. And all of that is entirely independent of the operating system. So these attributes and others are why the BIOS and/or the UEFI are regarded as firmware. In this video, we'll take a look at two of the most primary components of a computer: the central processing unit, or CPU, and the random access memory, or RAM. Now, these components are not also critical in terms of functionality, but they both also largely determine the overall level of performance for your system. Now, that said, there are certainly still other factors that will contribute to the level of performance, but suffice to say that if your CPU and memory are performing poorly, then it wouldn't matter if every other component was operating at peak performance. Your computer would still perform poorly. Now, I generally like to say that the CPU can be thought of as the brain of your system because it's responsible for executing the instructions submitted to it by the applications and services we run, and it essentially controls all other system operations, in that there really isn't any aspect of your computer's operation that doesn't involve data passing through the CPU. Now, just to be a little bit nitpicky, so to speak, it is worth mentioning that there are other devices that have their own processors embedded within them that can offload much of the work required by the CPU. Most notably, video cards have what's known as a graphics processing unit, or GPU, which, as their name indicates, can handle the rendering of graphics. But without a CPU, your system wouldn't function at all, regardless of how much work the CPU can handle. So it's still fair to say that all system operations are controlled by the CPU. The primary components of a CPU include a clock frequency, which refers to how many processing cycles can be completed per second. Again, at the risk of dating myself, when I began my career in IT, speeds were measured in the low megahertz values, where 1 megahertz is 1 million cycles per second. So the systems I was supporting at the time were higher than that. They were around 33 to 66 megahertz, whereas systems today are maybe around 2 to 3 gigahertz. So whereas 1 megahertz is 1 million cycles per second, 1 gigahertz is 1 billion cycles per second, which on its own is 1,000 times faster. So remarkable increases in processing speed have been achieved. The control unit is responsible for fetching, decoding, and executing instructions from memory, and issuing the signals that control the operation of other hardware. The Arithmetic Logic Unit, or ALU, is responsible for handling mathematical calculations and logic operations, such as evaluating yes, no, or true, false decisions. And the registers are small amounts of fast storage that are easily accessible by the CPU so that any given instruction or operand can be held until the complete instruction is executed. For example, any given instruction might require the contents of multiple registers to complete the operation. The cache refers to a small amount of high-speed RAM built directly into the processor, which, like registers, can be used to temporarily hold data, but the amount of cache, while it will vary from processor to processor, would be measured these days in megabytes, whereas any given register would only be 32 or 64 bits, depending on the platform of the processor itself. But the cache is commonly used to hold data and instructions that the processor is likely to use, which helps to reduce processing time by not having to wait for that information to be fetched from memory. Now, this process is typically referred to as prefetching, whereby the CPU quite literally guesses as to which resources might be needed to complete an execution. So there is a small risk of the CPU being wrong, so to speak, but when correct, it means that the results can be produced much more quickly because the resources required are already in the cache of the processor, so they don't have to be loaded from memory. Buses provide the communication pathways between the processor and the memory, as well as to other components. But there are three primary buses known as the address bus, which provides addressing information to various input and output components so that data can be located quickly in memory, the data bus, which carries the actual data among all of those components, and the control bus, which carries signaling information such as the clock cycles. The architecture refers to the number of bits that can be processed per clock cycle, and they include 32-bit, and 64-bit. Now, these days, almost all processors are 64-bit, but you might still encounter some older systems with 32-bit processors. But apart from the fact that a 64-bit processor can handle twice as much data per cycle, the more notable feature is the amount of memory supported by each, because a 32-bit processor means that it can handle 2 to the power of 32 possible memory addresses, which is approximately 4 billion addresses. Now, that might sound like a lot, but each memory address only holds 1 byte of data. So with 4 billion bytes of addressable memory, 32-bit processors, to this day, cannot have more than 4 gigabytes of RAM installed. Now, for years, this was way beyond adequate, but not anymore. So 64-bit processors can handle 2 to the power of 64 memory addresses, which is an incredibly larger address space. And it's important to note that in this case, it's not twice as large as the 32-bit address space. 64 bits of data per cycle is twice as much information as 32 bits, but 2 to the power of 33 is twice as much as 2 to the power of 32, and 2 to the power of 34 would be twice as much again. So by the time you get to 2 to the power of 64, that number is enormous. Hence, 64-bit processors, at least in practical terms today, can support an almost unlimited amount of memory. But with respect to more practical values, it's not at all uncommon to see computers with 32, 64, or even 128 gigabytes of RAM, with some of the highest level network servers or so-called supercomputers approaching or perhaps already using 1 terabyte or even more. But again, theoretically, far, far more memory could be addressed by a 64-bit processor. As for the specific types and/or applications for CPUs, there are 3 primary categories with respect to the types of systems into which they're installed: desktop systems, laptops, and servers. Now, for most of us, desktops and laptops will often be used for similar purposes in terms of day-to-day operations, such as a work computer or even a home computer, but the CPUs in desktop computers can typically have better performance specs as compared to a laptop, due almost entirely to the extra space and better cooling that can be implemented in a desktop system. Laptops, of course, are designed for portability, so small and light are the defining characteristics. As such, laptop processors typically have to be scaled back to fit into the smaller spaces, and most notably, they can't run as hot due to the limited airflow of a laptop. The primary concern for network servers, however, is almost always performance, so they're scaled up to ensure that servers can handle the workloads of servicing the requests of any number of client systems. And in many larger scale servers, multiple physical processors are installed for even higher performance. But it's worth noting that even if you do want to build a very high-end computer, for example, those used by gamers, server-class processors would not be the best choice because they're usually designed with what's referred to as back-end processes in mind, whereas games and other demanding applications are front-end services. So to clarify that, if I sit down at my computer and I want to pull up a web page, my computer has no control over how quickly the information from the web server can be delivered. That's dependent on the web server itself and, of course, all of the networking components between us. But what I do want is for my computer to load the browser itself as quickly as possible and to process the information that it does receive as quickly as possible. So my processor is more finely tuned for that type of processing. And because all of that happens on my computer, that's referred to as the front end. It's literally what I see in front of me. But the server that hosts the web page does not have to load a browser at all, nor any other application. Its job is to simply feed me the data of that website. But of course, there could be thousands or even millions of other people all wanting to view that same page. So it just has to sit there and deliver that content over and over again to everyone that requests it. But that all happens behind the scenes, so to speak. So those are back-end operations. So coming back to the gamer who wants a very high-end system, they want that performance dedicated to front-end processing, not back-end. Now that all said, there are processors and other resources that are available specifically with gamers or other types of enthusiasts in mind, but server-based processors, while very powerful, are designed for that performance to be directed toward back-end processes, so they just aren't suitable for desktop systems. Common CPU types include what's known as the x86 and or the x64 architecture. Now, the x86 platform was initially built by Intel and based on one of their earliest models known as the 8086 processor and a close variant, the 8088. Now, those models go back decades to the late 1970s and early 1980s, but from those models arose the 186, 286, 386, and 486. And in fact, the Pentium processor, which was released in the mid to late 1990s, was originally going to be called the 586. So the X simply represented that first value, but it could be any value. So the X simply represented that first number, whatever it might be. And as you might imagine, each increment in that value indicated a more capable processor. But all of those were 32-bit processors. So by the time the 64-bit became the standard, there were many other characteristics that determined the overall performance specifications, so the X was retained purely for recognition purposes, but x64 refers to all varieties of 64-bit processors. It should also be mentioned that Intel is not the only manufacturer that uses that type of architecture. A close competitor of theirs, known as Advanced Microdynamics, or AMD, also uses the same fundamental architecture, but they simply can't advertise them with those X distinctions. Now, that doesn't mean that you can just swap out an Intel chip with an AMD chip, but virtually any operating system or application that is supported by Intel would also be supported by AMD. ARM stands for Advanced RISC Machine, where RISC is RISC, which is also an acronym for Reduced Instruction Set Computing. And their processors have come to dominate the world of mobile devices, such as smartphones, tablets, and other handheld or wearable devices due to their lower power consumption and low heat generation. And Apple Silicon is, of course, implemented by Apple, but it's largely based on ARM technology for use specifically with iPhones, iPads, iPods, Apple TVs, and Apple Watches. But even Apple's larger devices, such as MacBooks, also use these processors. But of course, even they still have limited space available due to their sleek design. As for RAM or random access memory, this is effectively your computer's short-term memory, in that any data in RAM is not retained permanently. That's where storage or your hard drive comes in. RAM is designed to be much faster than hard drives, particularly traditional hard drives that still use a spinning disk, because RAM has no moving parts. It's simply divided up into addresses so that the CPU can find data based on its address. Now, these days, of course, solid-state drives are very common, and they also do not have any moving parts, but RAM is still accessed faster because there is a direct communications pathway known as a bus between the CPU and the memory, and CPUs and memory are also synchronized in their clock speeds these days, so in short, accessing RAM is much faster than accessing any kind of storage device. But coming back to the aspect of short-term or temporary memory, any data that is in RAM requires power for it to be retained, whereas hard drives and solid-state drives do not. So each time your system reboots, the contents of your RAM are entirely cleared. I tend to say that a good way to think about RAM is to imagine it as your desk, whereas your hard drive or storage is a file cabinet, in that the file cabinet contains every file that you have. But when you need to work on a specific file, you retrieve it from the file cabinet and you work on it at your desk. But then when you're done with it, you put it back in the file cabinet. So that's similar to your memory being cleared. In short, the contents of your RAM represents what is being worked on right now. But in that regard, the more RAM you have, the larger the workspace you have. So in other words, going back to my desk analogy, as long as you're an efficient multitasker, a larger desk means that you can work on many files at once. Or to put that another way, if you only had a very small desk and you still had to work on many files, then you'd be constantly going back and forth between your desk and the file cabinet to retrieve each file as you needed it, because there just isn't enough space on your desk to work on all of them at once. So this led to a little bit of a misconception back in the earlier days when people were commonly upgrading the amount of memory in their system, in that many would say, I need to get more RAM to speed up my computer. Now, while that was the apparent net effect, it's not really that more memory made your system faster. It's that not having enough slowed it down, because your system was continually swapping files between RAM and the hard drive. So by adding more RAM, that swapping could be significantly reduced. And again, it wasn't so much that your system sped up, it just allowed it to work at its optimal level. There are three primary types of RAM, known as static RAM, dynamic RAM, and synchronous dynamic RAM. Now, both static and dynamic memory are still used as RAM, and both have been in use really since the first PCs were introduced, but the difference between them comes down to their power requirements. I mentioned earlier with respect to storage devices how they, of course, can retain data when there is no power, but that's not the case with memory. Data in memory is lost when the power is lost, but dynamic RAM uses capacitors to store data, and capacitors only temporarily store electrical energy, so the power for dynamic RAM needs to be constantly refreshed for data to be retained. Static RAM uses transistors, and while power must still be present for data to be retained, it does not need to be periodically refreshed. Now, there are many other characteristics that distinguish the two, but in short, static RAM offers better performance than dynamic, since its power does not need that constant refreshing, but as such, it's more expensive, and it's better suited to only storing small amounts of data. Conversely, dynamic RAM might not perform quite as well, but it's less expensive and better suited to storing larger amounts of data. Hence, the memory that we all think of whenever someone talks about the RAM in their computer is dynamic. Static RAM is typically only used for small caches, such as the cache memory in the processor that was discussed earlier. Now, SDRAM is still dynamic, so the synchronous aspect refers to it being in sync with the clock cycle of the CPU, which in fact was not the case prior to SDRAM. Memory and the CPU each had their own clock cycles, which could cause bottlenecks in terms of overall throughput. But with the clock cycles synchronized, those bottlenecks can be reduced or even eliminated. All modern iterations of RAM these days are variations on SDRAM, but other factors such as DDR, which stands for double data rate, which itself means that data could be pumped twice per cycle instead of just once, dramatically increase the performance of current memory, and that DDR process itself has also been incremented to DDR2, 3, 4, and even 5, with each increment effectively doubling the data rate of its predecessor. In short, if you're considering a purchase or looking to assemble a custom system, you'll likely want the highest performing processor and memory. But of course, higher performance also means higher cost. But you'll also need to ensure that the processor and the memory are compatible, and that ultimately they meet the demands of what you need out of your computer. In this presentation, we'll provide an overview of the two common types of storage used in computing environments, which provide us with the means to store essentially everything we need for our computers. And we'll begin with what is typically referred to as the hard disk drive. And just before we get into its characteristics, I do want to touch on why they're called hard drives. And this refers back to the earlier days of computing when, for portable storage, we often used small disks that we could carry around easily that were made out of the same kind of material as music cassette tapes and or VHS tapes. Now, I realize that some younger viewers may have never encountered either of those, but they were literally long, thin strips of a plastic tape that was coated with a magnetic material, and information was stored by applying an electric charge to the magnetic material. So those portable disks just mentioned were made out of that same basic material, but they were a little thicker and more rigid and formed into a round disk instead of a long tape. But the disk itself was still quite flexible, hence they were dubbed as floppy disks. The two primary sizes were 3.5 inch and 5.25 inch, typically used as the A drive and the B drive respectively. But I haven't seen or used either of those in probably 20 years or more, so it's unlikely that you'd encounter even an older system these days that still uses them. But nonetheless, the hard disk, as its name indicates, stores its data on solid metal platters, which are, of course, very hard. Now, the term platter is used in this case because the entire unit typically had more than one disk inside of it. So the overall unit is typically referred to as the disk, but it would have multiple platters. And some earlier units had as many as 8 physical platters, but for the most part, the hard drives installed into any given PC throughout the last 20 to 25 years usually had 2 platters. But each side of the platter could be used. So with 2 platters, there were 4 surfaces on which to store data. Now, information was similarly written by applying an electric charge, and the metal used is still magnetic, so hard drives can store that information without requiring any power. So all hard drives provide non-volatile storage, which, by the way, is the opposite of the memory we use for RAM, which does require power to retain data. So anything that is in system memory is cleared each time the system is powered off. But clearly that can't happen with respect to all of the data we need for the computer to operate. In other words, it would be rather inconvenient, to say the least, if your hard drive was wiped clean every single time the computer rebooted. So then, what does it mean to say that they store all the data of our systems? Well, exactly that. The operating system itself and everything it contains is installed onto the hard drive, as are all of the user applications we run and every document that we create or receive. In earlier presentations, specifically when comparing storage to memory, I've often likened the hard drive with a file cabinet because it contains every file, whereas memory would be similar to your desk, where you work on only the files you need at any given point in time. But quite literally, at least in terms of functionality, every necessary file is stored on the hard drive. Now, clearly, you have some other options with respect to storing your own personal documents. For example, you might store them on a flash drive or burn them to DVD, but more than likely, they're on your hard drive as well. Now, since your hard drive itself is a replaceable unit, it requires a way by which it can attach to your motherboard, which is known as the interface type. And hard drives have gone through several different interfaces over the years, beginning with a standard known as Advanced Technology Attachment, or ATA, which actually comes in two varieties: serial ATA and parallel ATA, also known as Integrated Drive Electronics, or IDE, and EIDE, which adds an enhanced to the term as improvements were introduced. Now, just quickly, at a basic level, serial refers to data being transferred 1 bit at a time, and parallel means that data can be transferred 8 bits at a time. So clearly, parallel transfers would seem to be faster. Well, although it might seem that way on face value, in fact, that is not the case, at least for hard drives. And for an analogy on this, think back to the days of grade school and fire drills. We were always instructed to leave the building in single file. So why was that? Because trying to do so in multiple lanes, so to speak, always just caused a traffic jam, because any given lane would never be in sync with any other. So trying to get, let's say, 4 lanes of people through something like a narrow doorway at the same time would inevitably just cause a bottleneck. With data transfers, the same issues can arise. If you're going to transfer 8 bits at a time, each over its own lane, so to speak, then they have to be perfectly timed and coupled with some kind of timing signal. So it was determined that much higher speeds could actually be achieved by simply switching to serial transfers, which eliminated the timing issues. Then just push that data through faster and faster. So much so that, especially these days, serial ATA significantly outperforms parallel. And by the way, the same thing happened with printers. Early printers used parallel transfers over what was known as an LPT port, which stands for Line Printer Terminal. But while you might not have given it much thought, when they switched to USB, well, USB is the Universal Serial Bus, which obviously uses serial data transfers. And all USB ports can transfer data much more quickly than LPT ports. In any case, if your system does have a hard drive, and it's even at least 10 to 15 years old, it almost certainly uses a serial ATA interface. The physical cable itself is also much smaller. Parallel cables were referred to as ribbon cables because they were quite wide and flat, and they had 40 separate wires internally, and likewise they connected to a 40-pin connector on your motherboard. And it was also quite easy to damage or at least bend those pins if you didn't get the connector aligned properly. But a serial ATA cable is only about a centimeter wide and uses a keyed connector that inserts into a plastic housing that can't be installed incorrectly, and there are just flat metal contacts inside the cable and the connector that touch each other when connected, so there are no pins to bend or break. The other common type of interface is known as Small Computer System Interface, or SCSI, which is actually pronounced SCSI in the world of technology. And SCSI has been around for a very long time, but it has also gone through many iterations and versions to increase its speeds and capabilities. But SCSI drives were and remain in use primarily for network servers, most notably due to the fact that the original ATA interface only supported 2 drives per interface. Now, most desktop computers would have 2 interfaces on the motherboard, a primary and a secondary, so with 2 drives per interface on 2 interfaces, you could have up to 4 hard drives in a desktop, but optical drives such as CD and DVD players also used the same interface. So the most common configuration, at least for a system purchased from a vendor, was to have 1 hard drive and 1 optical drive. Then you could optionally add up to 2 more of either if you wanted, but from day one, the SCSI interface could support up to 8 devices, with later revisions supporting up to 16. Now, the motherboards did not have 8 physical connectors on them, but you could install a single card into one of the expansion slots known as the SCSI controller card, which is required to use with SCSI, but even that did not have 8 connectors because the drives could be daisy-chained in sequence. In other words, they could all be connected to a single cable that simply had multiple connectors on it. Now, the controller card itself also counted in terms of the total, so with original SCSI, you could have the controller card, then up to 7 drives. In later versions, the card still counted, but you could then have 15 drives. So servers with SCSI interfaces could store far more data in terms of capacity. SCSI also supports what's known as hot swapping, which means that you can detach and reattach a drive without shutting down the system, which was also rather necessary for servers because if you do have, let's say, 15 hard drives in your server, then the chance of any one of them failing is much higher than if you just had one hard drive. So shutting down the server to replace it can cause lengthy disruptions to normal operations. So hot swapping avoids that problem. And it's also worth mentioning that the SCSI interface was significantly faster than the original ATA specifications, although current serial ATA specifications are keeping pace with SCSI. And also just with respect to the number of drives, serial ATA only supports a single drive per connector, but the connectors are so physically small that you can easily have many of them on any given motherboard, and you can also still purchase a single controller card, which could also house multiple connections. So you can still install multiple physical serial ATA drives into a desktop computer. It's just not an overly common configuration. As for their basic functionality, as mentioned earlier, most hard drives contain 2 physical platters, and each surface can store data, and the entire assembly spins on a central spindle at very high rates. Common spin rates were 5,400 revolutions per minute, which was typical for laptop hard drives, and 7,200 RPM for desktop hard drives. Although some high-performance drives reached speeds well above that, but they were the 2 most common speeds. Then there is an actuator arm that moves back and forth with read-write heads that apply and sense the electrical charges to each surface. Now that read-write head floats above the surface, so to speak, but very, very close to it. But it doesn't physically make contact, and if it does, it can cause damage. So this was referred to as a head crash, which is largely where the term crash came from when your system fails for any reason. Now, while hard disk drives are still in use, they're rapidly being replaced by solid-state drives, which, unlike hard drives, have no moving parts. Hence, they offer significantly higher performance, but as such, they are more expensive than hard drives. But the cost has come down significantly in recent years, to the point where it's almost worth it to have a solid-state drive as the primary drive of any system, especially in a laptop, which are more susceptible to being dropped while they're being transported around. The impact of a drop could damage the moving parts of a hard drive, but that's not an issue with a solid-state drive. So, with no moving parts, solid-state drives store data using the same type of static memory found in flash drives. So, they're, in essence, just larger versions with higher capacity. And since they don't use a spinning disk, the read-write speeds are always steady and consistent. With a spinning disk, access is always fastest around the outside edge, because the outermost edge covers the largest distance with each rotation, whereas the innermost section covers the smallest distance with each rotation. But any given rotation still takes the same amount of time. So if you're covering a larger distance in the same amount of time, clearly you're moving faster. So hard drive transfer rates are effectively an average value overall. This also translates into much faster boot speeds because the data need only be located within a specific address, and nothing has to be moved to access that data. Just as a real-world example, the last system I owned with a hard disk drive took about 1 minute and 45 seconds to fully boot into the interface of the operating system. My current laptop with a solid-state drive does so in about 13 seconds. So to finish up, despite the improved performance features of solid-state drives, again, hard drives are still in use, primarily because they're still cheaper. So larger organizations in particular will often use them for data archives or backups, data that is still needed, but accessed only infrequently, and also to create tiered data storage services for things like cloud storage. subscribers can pay more for the higher performing storage when needed, but similarly, they can save money by using hard drives for data that only needs to be archived. So, like many things, the choice of drive type will be dependent on your needs. But if you're considering the purchase of a new system, I certainly recommend that you spend a little bit extra and go with a solid-state drive. In this video, we'll take a look at the Graphics Processing Unit, or GPU, which, as you might guess by its name, is used to produce high-quality graphics and video rendering. Now, just to quickly address a bit of a possible misunderstanding, the GPU itself is not the same thing as a video card, but you might hear the terms used somewhat interchangeably. But just as a very basic distinction, think about the CPU. That in itself is simply a chip, but it has to be installed onto the motherboard to be of any use. And on the motherboard are various other components that all contribute to processing data. Likewise, in the case of a video card, the GPU is a chip that is installed onto the card, but like the motherboard, there are other components on the card that also contribute to processing the graphic information. So, in short, the GPU is simply a component of video processing. It's not the video card itself. Now, on that note, video cards and their associated GPUs came about in the first place because video has become such a demanding process in computing these days. Now, to clarify that, there, of course, has always been a video component to any computer going back to the earliest PCs, because, of course, we needed to see what we were doing. But in those early systems, the displays were basically black and white, and everything was mostly just text-based. So the video aspect was more or less handled by the CPU and a reserved portion of the standard system memory. But of course, these days we have extremely advanced games which require constant refreshes of the images on the screen, 3D graphics, computer animation, and/or computer-generated imagery or CGI. So that kind of processing is very demanding. So dealing with it has effectively been offloaded from the CPU to the GPU. Now, it's also worth mentioning that despite the term graphics processing unit, its advanced capabilities have also been tapped for other demanding processes such as artificial intelligence, machine learning, and cryptocurrency mining, among others. Now, earlier I mentioned how the GPU is a component of the video card, much like the CPU is a component of the motherboard. But in some cases, there still might not be a video card, in which case the GPU is integrated directly onto the motherboard. Now, this doesn't change its functionality at all. It's still responsible for processing the graphics information. It simply means that a separate video card is not required. But while that will certainly function for most users who are just using standard Office-type applications, it's almost never adequate for gamers, graphic designers, and other enthusiasts. So the other option is the separate or discrete graphics card, normally just referred to as the video card. This is quite literally a separate circuit board that installs into one of the expansion slots of the motherboard and contains all graphics-related components within it, including dedicated memory so that they don't use up standard system memory. Now, even if your system does have an integrated GPU, you can still install a discrete card, and the integrated will still function if you want to use it, but most people who choose to install a card are doing so because the integrated unit simply doesn't provide adequate performance. But despite their lower performance, integrated GPUs are still very commonly used, particularly in laptops or other smaller devices, clearly for the space savings, which facilitates more portable systems. And again, even on desktop systems, for office environments or even home computing where gaming or graphics design is not a concern, integrated GPUs are generally adequate. Now, I should mention that there are gaming laptops which do use integrated components, but the GPUs are still more advanced along with the associated resources. But what you'll generally find is that the entire laptop itself is physically larger, and it usually includes additional cooling because all of that advanced processing generates more heat. So while they do perform well, if you're looking for a laptop that is small and light and good for travel, then a gaming laptop would not be the ideal choice. So, if you feel that a discrete GPU/video card is the better option for you, then it will almost certainly offer far more processing power than anything you would find with an integrated unit. But you need to be mindful of the available space within your system. You'll need to verify the availability of an appropriate expansion slot, and modern video cards also include large fans to provide cooling, so it's possible that they might actually require the space of 2 slots, depending on the configuration of your motherboard. But motherboard manufacturers are certainly aware of this, but it's still something that you should at least check. Just for reference, to finish up, a high quality gaming video card these days might be up to 9 or 10 inches long by 4 to 5 inches wide by 1 to 2 inches thick, including the cooling. And the absolute highest level cards can easily cost many thousands of dollars in terms of price. So be sure that it fits into your budget as well as your physical computer. In this video, we'll provide an overview of cooling your computer system, which is a significantly important consideration when it comes to computing because, in short, the internal components, such as your CPU and GPU, have electric currents running through them at a very high rate, which unfortunately has the side effect of producing a lot of heat, easily enough for those components to physically burn if they aren't adequately cooled. So clearly, any component that overheats can become permanently damaged, but manufacturers are of course fully aware of this possibility, so most computers will have fail-safes built in to prevent overheating by throttling back various components to lower the temperature in the event that the cooling systems have failed, or in more extreme cases, the system might shut itself down entirely. Now, you clearly don't want either of these situations to happen, so ideally, it's better to at least keep an eye on the cooling elements from time to time to ensure that they are working as expected. Now, by far the most commonly implemented cooling device is a fan, and in larger desktop systems, it's not uncommon to find several of them, including one for the primary power supply, one or more for the primary case itself, one directly on the CPU, and one or more directly on the GPU. The fans in the power supply and usually the case tend to be larger, usually around 4 to 5 inches in diameter, and those directly on the CPU and or GPU are usually around 2 to 3 inches. For the higher performance components such as the CPU and GPU, it's also not uncommon to find liquid cooling systems whereby water is pumped through small pipes that contact the primary components to dissipate the heat more quickly. Water can, in fact, dissipate heat much more effectively and efficiently than blowing air, but of course they're more expensive and can require more maintenance overall. But of course liquid cooling is more expensive and it can require more maintenance overall, but it can also allow your devices to perform at higher levels and for a longer time. Now, graphics cards are one of the most common components that require special attention to cooling simply because GPUs produce a significant amount of heat due to the nature of processing video data. So almost every video card these days will include a fan or possibly even 2, but separate third-party cooling systems can also be purchased to enhance the cooling, thereby improving its performance. But again, this level of cooling is more commonly found among gamers and specialty systems. Most standard level GPUs, for lack of a better word, will perform adequately with just the included cooling. That said, CPUs and GPUs are not the only components that produce heat. There are several other components within the system that can contribute, including the memory, the storage devices, and even devices such as a sound card, depending on their level of activity. Now, none of them would get as hot as a CPU or a GPU, but if they're all producing some level of heat, then of course the entire system is just going to continue to get hotter and hotter. So other cooling devices are often found on some internal components, such as heat sinks, which are effectively just radiators that are physically mounted directly onto the chips themselves, and they're usually made of a very conductive metal to help dissipate the heat more efficiently. And they also have many large fins, so to speak, which significantly increases the surface area, which again allows the heat to dissipate more easily because the same amount of heat is spread out over a much larger area. Most CPUs, in fact, have a heatsink mounted directly on top of the chip itself, then a fan mounted on top of the heatsink. And on that note, Of course, we mentioned fans already, but the direction of airflow is also an important consideration because you don't want to be blowing hot air off one component and onto another. So most systems are in fact designed with airflow in mind, so the hot air can be evacuated directly out of the system entirely while also drawing air in from the cooler surroundings. Considerations with respect to maintaining adequate cooling include dust and dirt, which again is an unfortunate result of moving air. It's inevitable that your system will pull in dust from the surrounding air, so be sure to clean your systems out regularly, ideally with compressed air that can reach into the nooks and crannies of your system, including between the fins of your heat sinks. Vacuums can be used in and around the case itself, but be sure to be particularly careful around the more delicate components. Again, the ideal approach is to use compressed air to blow out the dust, but then with a vacuum placed close by to draw in whatever comes out. If you're building your own system, then try to place various hardware components as far apart from each other as possible. For example, if you have 2 hard drives but 4 bays, then put one in every second bay, again to maximize airflow, and try to leave an empty slot between your expansion cards as well if you can, and try to route cables as efficiently as possible, perhaps even tie wrapping them together, because if the interior of your case is just a random mess of cables, that will deflect and disrupt the airflow. Now, all of that said, while cooling is a significant aspect of maintaining your system, it's typically not something that has to be attended to daily. But I would suggest checking the inside of your case at least monthly to ensure that no significant dust or debris has built up. But I would also suggest increasing that frequency, particularly if you have pets that shed, or if there might be any source of moving air nearby, such as a heating duct or an air exchange vent. Again, unfortunately, moving air tends to draw in dust. So if any of those situations are applicable to you, certainly pay a little more attention to cleaning and keeping your system cool. For our final video of this course, we'll examine the role of the Network Interface Card, or NIC, which is also commonly referred to as an Ethernet card or a network adapter, but regardless of the term, the functionality is the same, and that is to provide your computer with the ability to connect to a network and all of their associated components and resources, such as servers, printers, switches, and routers. Now, it might be in the form of a physical cable connection, or in the case of Wi-Fi, by connecting to the appropriate network access point, but in either case, without a network adapter of some description, your system will be effectively isolated from all others. Now, the network interface can be in the form of an internal or an external device, and very much like the graphics processing unit that we discussed earlier, it can also be in the form of an integrated chip on the motherboard itself, or it can be a separate expansion card that is installed into one of the slots. As for the external versions, they primarily come in the form of a USB device that you simply plug into any available USB port. Then there would also be an Ethernet port for the cable, or if it's wireless, of course, it would just contain transmitters and receivers. But just as a quick example, the laptop I'm using right now does have a built-in Wi-Fi adapter, but it does not have an integrated Ethernet port. So if I want to use a wired connection, I do have a USB adapter, which is essentially just a short cable with a USB connector on one end and a small rectangular housing on the other with an Ethernet port. It's very small, light, and portable, and can easily be carried around in my laptop case. Now, just quickly coming back to the video card, the use of any dedicated video card as opposed to the integrated GPU is almost always for the significantly better performance they offer. But as far as network interfaces are concerned, that's far less of an issue. Network communications aren't nearly as demanding as something like processing graphics information, so in many cases, the integrated network adapter is more than adequate. So dedicated cards are becoming less common these days. They were a virtual requirement back when I began my career in IT because almost no motherboards offered them as an integrated component, but it would be quite rare these days to find a system without some kind of integrated adapter, but you would likely still see them in use for systems such as network servers that might have connections to multiple different networks, or those with redundant connections that are used as backups, or those that connect to different types of networks using different technologies. For example, one adapter might connect to an Ethernet network with a standard cable, but then another might be installed to connect to a fiber optic network. Or perhaps you might have a desktop system that has been in use for quite some time, and the integrated unit might be present, but it might not support the speeds of today's networks. So you might simply upgrade that system by installing a separate adapter. But by and large, integrated interfaces are very commonly used these days. As mentioned a moment ago, wireless adapters are also able to provide the exact same type of network access. They simply do so by using radio frequencies as opposed to a physical cable. Now, almost all laptops and other mobile devices these days come with an integrated wireless adapter, but if for any reason that should fail, or if you happen to have an older device that does not have an integrated interface, then you can still install an external adapter, which might also just plug in using a USB connection. But there are also desktop wireless adapters that can be installed internally as expansion cards, just like those mentioned earlier. But instead of an Ethernet port, they would likely have an antenna to improve its ability to transmit and receive, and these can be a great option for a home desktop computer that's placed in a location that does not allow you to run a physical cable to the access point, such as when the two are on separate floors from each other. One final consideration that is certainly worth mentioning with respect to any network connection is the speed supported by the adapter. Now, the speed of any given network itself might not be within your control. For example, if you are just connecting to a public Wi-Fi, then you have no control whatsoever. And if you're on a corporate network, then the overall network would be implemented and maintained by your system administrators. But of course, for services such as home internet, you can usually choose various speeds from your provider. So ideally, the adapter or the system itself you purchase should support the speed of the network. Wired networks then indicate their speed using a category and a numerical value. So the term Cat5 is simply short for Category 5. And just for reference, the earlier categories do exist, but Category 1 is standard phone cable, so not even suitable for network communications at all. And 2, 3, and 4 exist as well, but they're exceptionally slow by today's standards. So about the minimum you might still find in use would be Cat5, which only supports a speed of 100 megabits per second. Now, that would be adequate even these days for standard internet browsing, email, and even corporate network activities such as transferring files and submitting print jobs. But for the more current activities such as streaming video, online gaming, and downloading media types such as movies, you would definitely want at least 1 gigabit per second, which requires at least Cat5e, where the E stands for enhanced. Now, Cat6 also supports 1 gigabit per second, but it has a higher frequency range and can support more data per cycle than 5e. So you can usually transmit more data in the same amount of time. So on that note, if you can transfer more data in less time, it would seem that Cat6 should be faster, but it's also worth mentioning that these speeds are more or less the theoretical maximum speed that could be attained. In practical implementations, however, those speeds are almost never actually realized. So you'd be more likely to approach 1 gigabit per second with Cat6 than you would with 5e, but their theoretical maximums are still the same. Cat6a stands for augmented, and it can support up to 10 gigabits per second. And as of the time of this recording, Cat7 and 8 do both exist, supporting up to 40 gigabits per second, but those kinds of speeds aren't common in most environments just yet. On the wireless side, you'll typically see versions including 5, 6, and 6E, which correspond to values known as 802.11, with specifications then defined by letters such as A, B, E, G, N, X, AC, AX, and others. And if you've ever wondered what 802.11 is all about, that actually came from a series of meetings and conferences that were held in February of 1980. So quite some time ago, but that's where the 802 comes from. And they initially designed 12 different specifications of ways by which you can network. And 11 defined wireless. Now, Wireless networking at that point in time was nothing like it is today, but it still did define the initial architecture of wireless networking. So that's what 802.11 is all about. Then the letters are simply refinements to those specifications, each with different speeds and characteristics. So as it stands, version 5 supports up to 3.5 gigabits per second, and 6 and 6E support up to 9.6 gigabits per second. Now, you certainly don't need to be familiar with every spec of every type of connection, but your network adapter should ideally support the maximum speed of the network for optimal performance. So it's certainly worth knowing what that speed is. Now, that said, if your adapter doesn't support the maximum speed, it will still work, just at the lower speed. In short, a network is only as fast as its slowest component, so try to ensure that your own network adapter is not the slowest component. So in this course, we've examined basic concepts surrounding computer devices and components. We did this by exploring network interfaces, devices and setup, graphic devices and peripherals, peripheral installation types, motherboards, BIOS and firmware, CPUs and RAM, and common storage types, GPUs, network interface cards, and computer cooling. In our next course, we'll move on to explore basic concepts surrounding internet access methods, storage, and the various types of computer systems.